In this video, we're going to explore how we can use differentiation to find the stationary points on a graph. For those who don't know me, my name is Chris. I've been tutoring math methods since 2023, and throughout that entire time, I've been sharing guides like this, covering the entire math method syllabus. So if you find this helpful, consider browsing the channel for any other topics that you might be struggling with. This one in particular is going to be a deep dive into the fundamentals of finding stationary points. In a later video, we'll then explore the applications as to how you can use this in your extended response questions. Let's get into it. Stationary points are simply a key feature of some graphs where the gradient of that graph is equal to 0 at that point. There are three kinds of stationary points that you'll come across. You have the local maxima, the local minima, and the stationary point of inflection. Up until now, you've likely come across all of these. The local maxima and minima are definitely there in your quadratics and some of your cubics, and the stationary point of inflection would have first been seen with that basic cubic. Inflection points are the ones that have the most variance in them. You can think of them as simply a spot on the graph where the graph wobbles. In this case, we have it going from concave down to concave up, but the reverse can also be true. So there's a few different ways that this could actually look. Just as long as during that transition, there is a moment where the gradient is equal to 0. And the reason why I specify this is because there are some inflection points, like we can see in the circular function here, where there is that wobble, but in the middle of that wobble, there is no gradient of 0. So that is to say that this inflection point is not considered a stationary point of inflection. So how do we find them? Well, the key feature of the stationary point is that it has a gradient of 0. And as soon as gradient-related information starts coming into play, that should immediately trigger in our brain that the derivative is going to be useful for this kind of question. The derivative of a function is an expression which helps us determine the gradient of the original function for any possible value of x. So basically, I plug in an x value into my derivative, and whatever comes out is the gradient of the original graph at that spot. So if we're interested in finding the stationary points, what we're going to do is set that derivative equal to 0. Because when you set derivative equal to 0, you now find where gradient is equal to 0. Once you've equated it to 0, all we're going to do is solve for x, thus finding the x coordinates where you have gradient 0, thus finding the stationary points. In this case, all we're going to do is a bit of factorization and null factor law to complete the solve. But as I said earlier, this is just going to find the x coordinates of our stationary points. We do also need the y coordinate as well if we want to have the full coordinate pair. So all we're going to do is take that x coordinate that we just found and plug it back into the original function. Not the derivative function, but the original one. Remember, the original function has x and y related information, whereas the derivative function has x and gradient related information. It's a very common mistake. I see people plug it into the derivative all the time by accident. All right, let's step up some complexity. This question, although looks more complex, is still fundamentally the exact same thing. We're still just trying to find where the stationary points are. So we're still going to follow the exact same procedure. Find the derivative, set it equal to 0, solve for x. The trickiest part of this, of course, is that the function is complicated. So let's dive into how we're going to handle it. First of all, finding the derivative is going to require the product law. We can determine this because we can see that our function is separated by two individual terms that have a multiplication symbol between them, or at least an implied multiplication between them. So, as per the product law, we're going to split those terms up into their individual sections and find the derivatives of each of those. From there, we have everything we need for the product law. So we just plug everything in where it belongs, and we have our derivative. The next thing we have to do from here is set it equal to 0, right? This is part of our procedure. There's the challenge. This function looks quite complicated. How could we possibly solve this for x? Well, first, we're going to have to figure out what type of function this even is. This function is actually a polynomial, and we can determine this because it is a bunch of x terms that have various constant powers. Remember, the n in this function isn't actually a variable, it's a constant. This is f of x, not any other variable. Knowing that this is a polynomial is quite strong. because it means that we solve this the same way we solve most other polynomials, via factorization. So let's look for any opportunities. We're going to notice that 2x minus 1 is a common factor of both of those terms. So we're just going to take out 2x minus 1, along with the highest power possible, out the front of the function, thus getting it into a factorized state. Why is that important? Well, when you have a factorized function that equals 0, we can now use the null factor law to solve for x. So we're just going to look at each of those terms individually, set them equal to 0, and solve for x. This is significantly easier on the left-hand side, because all we're doing is taking the root of whatever that power would have been. On the right-hand side, we're going to have to do a bit of grouping to get things into a solvable situation. As a quick reminder, we don't actually need the y coordinates for this question in particular, since it's only asked us to find the x coordinates. But if you did need them, you would simply take the x coordinates that you've just found and put them back into the original function, which would be kind of complicated, so you can see why this question didn't actually ask us for them. Real quick guys, if you've been finding these lessons helpful and would like more support like this, I actually have written versions of these lessons available on my website. They're nice little self-contained modules that go into detail into all the key questions that will come up for that particular topic. There's even a nice summary at the end which you can print off and chuck into your bound reference nice and easy. And if you're looking for more personalized support, you can also apply to join either our group classes or our private classes. You can give them a try risk-free for the first 3 weeks and see how you like them. So be sure to give that a look. Anyway, back to the video. Okay, now we know how to find stationary points, but that only tells you where they are, not what type of stationary point they are. Remember, there's 3 different types. You've got your maxima, you've got your minima, and the inflection points. None of what we discussed so far tells you what type they are. And yes, if you could sketch the graph, then by all means go ahead and do that. For most functions that are sketchable, this will be the most effective way of doing it, because you just see it on the graph. You can clearly see that one is the maxima, that one is the minima, that one's the inflection point. Some functions, like the one that we saw earlier, are a bit more challenging to sketch. So what we're going to have a look at now is a general purpose way to solve the nature of the stationary point for all types of functions. And that is going to be the second derivative test. First, for the sake of time, let's assume we already know where the stationary points on the function are. You already know how to solve this, so we're just going to skip those steps. If we want to find what type of stationary point they are, our first step in the procedure is going to be to find the second derivative, which simply means taking our derivative function and finding the derivative of that derivative function, which in this case is going to get us to 6x. Once we have that second derivative, we're going to take the x coordinates of the stationary points and put them into the second derivative and simplify all the way through. Once we've done that, we can now determine what type they are based on if we had a positive number, a negative number, or if it equaled 0. If the result was negative, you have a local maxima. If the result was positive, you have a local minima. And if the result was 0, you likely have a stationary point of inflection. And I do say likely because technically speaking, that doesn't always get you to a stationary point of inflection. But as far as math methods is concerned, it'll work perfectly fine. This is more so for anyone doing special math. There are a few more nuances to that. So if we look at our results, we can see that x equals -2 gave us a negative result. Therefore, we had a local maxima. And x equals +2 gave us a positive result. Therefore, was the local minima, which once again we can see is validated on the graph. That's about it for this one. If you want to see how you can apply these concepts to those external response style questions, then be sure to click the next video that pops up. I'll even leave a link in the description in case that breaks for whatever reason. And again, if you feel like you need more support, whether it be more classes, more access to resources, practice tests, any of that, be sure to check out our website and apply online.